In this segment, I'd like to start with a thing that's familiar, or at least that we've seen before, and move away from that a little bit to something that sort of looks like it, is inspired by it, but that we can sort of pick up and run with and go much farther. In this segment, I'd like to introduce Boolean algebra. That's what this segment is about. In the next segment, we can talk a little bit more about, all right, once we have an algebra, we can talk about functions, right? Because that's what happens in traditional math, right? We start with algebra and we eventually have X, Y, Z, and so on. And then we can talk about setting Y equal to f of X, some function that determines the value of one of the variables, Y, given the value of the other, X. And so we can start to build these functions that do things, that represent ideas in terms of Boolean variables. But before we get to that, first we've got to introduce the algebra that we're going to use to build those functions. So let's start with the table in red marker, and let's think about the thing that we have become familiar with over the last week or so, and that's binary arithmetic, where these are numbers that are behaving like every other number we have ever tried to add or multiply, and we express the answer in a binary number system. This table is all about numbers. It seems obvious, but the other one isn't. So I want to set this one up. This one is about numbers. Let's make sure that we understand what's going on. Suppose we have two numbers. Call them X and Y, just so that we can keep them straight, which is which. If X has the value of 0 and Y has the value of 0, we could add these two numbers. And we've done this trick. We did it on the worksheet, right? We said X is some binary number, Y is a different binary number, and we added them. And we added them arithmetically using a binary numbering system, and we got answers, and we said, okay, we're done. We added them. Great, so let's do the same thing. And we could also talk about the multiplication of these two numbers, X and Y. We said that binary multiplication works just like, traditional base 10 multiplication that we're used to. The sort of partial sums, shift and add, that kind of thing, where you move each next digit over and then you add up all the things. That works the same way in binary because it's just a different way to write a number. All of the sort of algorithmical tricks that we use to multiply two numbers work just fine in binary. So this is familiar to us. We know how to add, subtract, multiply, divide. If we add 0 and 0, we get 0. If we add 0 and 1, we get 1. If we add 1 and 0, we get 1. If we add 1 and 1, we get 2. Note that this is not 10. It's 2 written as a binary number. Okay. If we multiply 0, 0, 0, the only time we get anything other than 0 is if we multiply 1 and 1. We get 1. Not super exciting, but definitely a thing that we can do. But then we start to think to ourselves that this looks like useful behavior. For example, notice that the value of the product of 2 bits, binary digits, the product of 2 bits is only 1 if both of the 2 bits have the value of 1. If we're talking about 2 bits, X and Y, and we want to multiply them, either X could be 0 or 1, or Y could be 0 or 1. We've got 4 possibilities. those four possibilities. And the only time the product is 1 is when both are 1. Both x and y are 1, the product is 1. And it makes me think that a binary product, the product of 2 bits, is a useful arithmetic operation because it helps to answer like a logistical question, a logical question. Is it true that both x and y are asserted value, have their signals asserted, that they are both on? The only time the answer is yes is when both x and y, whatever they turn out to be, and I'm not really sure yet, but if x is some sort of signal, like channel 1 on an oscilloscope, and y is the other channel, anytime it's true that both of those signals have their on value, their high values, their sort of, yes, this signal is asserted values, this question answers yes. And any other time, if if they're both low value or if only one of them is high, then this question says no. The only time that this yes or no question answers yes is when both signals have their high value, which we've been calling signal asserted or on, right? And then I start to think about other sort of characterization questions that I could ask about x and y. All right, so we can say, is it true that both of them are asserted? We could answer that question. What about, is it true that at least one of them is asserted? It doesn't matter which one, or if both are, just as long as at least one is asserted, answer that. And then was okay. Well, if they're both 0, then neither of them. So it is not true that there is at least one that is asserted. So we say no. But in the other 3 cases, yeah, at least one of those 2 signals is in its asserted state. In the fourth sort of state here, both of them are, but that's fine. It's still true that at least one, 2 is greater than 1, so at least one has its asserted value. And we could answer other logical questions, other yes or no questions. Like, well, we could say, okay, is it true that neither of them, that none of them are asserted? And it would look like, yes, for this state, it's true that neither has its asserted value. And then for the others, the answer would be no. Because in each of these states, at least one of them is asserted, so it isn't true that neither of them is asserted. We could answer other question, is it true that either one or the other, but not both, is asserted, and so on and so forth. And we could answer these yes or no style questions about these 2 sort of signals, x and y. And I guess that would be neat. We'd have tables of yeses and nos. But then I start, because is it true that both x and y are asserted? And we answer, we say yes or we say no. But those are the 2 things we can say. Either yes, it's true, or no, it is not. That the that the answer to a logical question like this has only two values, only two possible values, either yes or no. And that's exactly the kind of thing that that turned us on to binary in the first place. It's a system that only has two states. The LED is either on or off. The answer to this question is either yes or no, which makes me think that we could describe these logical questions and the answers to them using binary, representing the answers to logical questions using two values, zeros and ones, I suppose, because we're already kind of using zeros and ones already. So here's my proposition. Anywhere where there was a no, let's put a 0. And anywhere there's a yes, let's put a 1. Now, the answer to the question, are both x and y asserted, is expressed in the same language as the individual sort of signals x and y. So we could, if we wanted to, we could treat this, the answer to this question, as its own separate signal. And later, we could say, is the answer to this question 0 or 1? Is the answer to this question asserted, representing the answer yes? Is the signal that represents the answer to this logical question asserted, showing yes? And we can treat the signal that is the representation of the answer to a logical question as its own kind of variable almost. And we could make a new table of, all right, let's take these values and combine them with something else and ask a different question about the combination. And we could start to sort of feed logical questions to each other. And we're talking inputs. We feed one value to a logical question, and the logical question gets an answer, and that's an output, I suppose. And we're talking about inputs and outputs, and we're talking about the different logical questions could, I guess, be represented by different, well, logical functions. Because it's with the fact that we're using numbers now makes me think that we could define and like a logical algebra, right? That anytime we want to ask the question, are both of these two values asserted? That there's a function, that there's a way to represent asking that logical question. Around the turn of the 20th century, late 1800s, early 1900s, a number of folks that were working in applied electricity and mathematicians as well, started to ask themselves very similar questions. It was in the 1800s, late 1800s, that George Boole, Boole, proposed an algebra of this type. In the 1930s, it was sort of reconfigured as switching algebra, which has a really nice sort of like intuitive sense to it. Think about the switch that turns the lights on or off. That the switch is a two-state sort of tool, and it's right in our wheelhouse, right? In the early 1900s, it was like 1904 or something like that. A mathematician proposed a set of mathematical postulates, sort of things that are going to be true about this particular system that we're sort of talking about developing. And the next step is to figure out what those are. (1854) is George Boole, and 1904 is the mathematician Huntington that developed these 6 numbered postulates of Boolean algebra. Boolean algebra, algebra in this system named after George Boole, is a system that uses 2 operators. Think like mathematical operators, like the square root operator. It's a symbol that conveys an instruction to do a thing. The plus sign, for example, for addition, is a symbol that conveys add these 2 numbers. We're going to use symbols that are familiar to folks doing algebra. So we'll use a plus, a T cross and a dot, a plus sign and the multiplication dot that are familiar to us. They don't mean addition or multiplication anymore. This is a logical proposition. We're not doing arithmetic. We are representing a logical algebra using these symbols. Why these symbols? Because they're familiar to us, because we're used to looking at algebra written with these symbols, and because there's no small amount of correspondence, and we'll see that in a second. These 6 things need to be true, and I'll just wait a minute and let you read through these 6 postulates, things that we agree are going to be true about our algebra system in order for it to be coherent and functional and not give us crazy results. Okay, so you've looked over these for a second. Closure it just means that whenever we operate on a set of binary, in this case, variables, on a set of algebraic variables, we aren't given a value that is outside the set of those variables. And I'll give you an example of what I mean. The set of even numbers is closed under addition, closed under subtraction, closed under multiplication. Take any two even numbers, add them, subtract them, or multiply them. The answer will be another even number. But division, right, is not necessarily closed for even numbers. If we take 18 and divide by 6, we get 3, which is not an even number. It's a number outside the set of even numbers, so it's not closed. Division is the set of even numbers is not closed with respect to the division operation. And that's what we're saying here, that the structure is closed with respect to these two operators. The element 0 exists, the element 1 exists such that these things are true. Both structures, both operators obey the commutative property. If we switch the order, they get the same answer. Both operators are distributable over the other one. And that's a difference from normal sort of numeric algebra. This statement is true for Boolean algebra as outlined in the Huntington postulates, but it is not true for ordinary numeric algebra. So that sort of helps underscore the fact that this is a different kind of thing. This is not a numeric algebra. It is a logical algebra. Okay, so the element 0 is an identity element with respect to the operation defined as the plus sign. Okay, x plus 0 is equal to x. So let's see if we can find in our table that something plus 0 is equal to the same something. That something plus 0 is equal to the same something. Or the other way around, because remember it has to be commutative as well. So 0, this sort of Huntington plus sign, 0 plus 1, 1, 1 plus 0, 1. I'm not sure about that, it's not. But if we try this trick with the other column, 0 plus 1 should be 1. So this column, I don't want to allow it to correspond to the plus sign operation because it doesn't fit with what Huntington's postulates say should be the behavior of the plus sign operation. 0 plus a thing should be the same thing. Okay. I think we're safe saying that this column represents this Boolean operation plus sign. It's not x plus y, not in a normal arithmetic sense. That's this. We're not talking about this anymore. In fact, I'm about to erase it. We're talking about logical questions, and we've got this new sort of binary operator T that has behavior according to that column. That if we allow the column that used to be the answer to the question is at least one asserted, if we allow that logical question to be attached in meaning to the Boolean T symbol here, that we can satisfy the postulates of the Boolean algebra. That the logical question is at least one of them one. Can do the job for us of the binary operator T that Huntington postulated. All right. Element 1 is an identity element with respect to the other operation. X dot 1 is equal to X. Something dot 1 should be equal to something. So this column isn't that. Same story here. Something dot 1 is equal to something. Well, this is our candidate. Other things we need are that X dot X apostrophe. Now, X apostrophe is what? The complement. Okay. Okay. For every element, there exists an element such that X, T, X apostrophe is 1. Okay. I'm looking at 5A here. X, T operator, X apostrophe equals 1. What if X itself is 0? If this column is representing the T operator's results, X, T operator something evaluates to 1 when the other thing that we are acting on with this T operator is 1. In a two-valued system, that's just not 0. Like if the only two values are 0 and 1, if we have the complement of 0, well, the thing that isn't 0. There's only one other choice. So apparently complement in this case just means the other variable, the other value of the variable, I guess, the other possible value. x dot x dot x apostrophe equals 0. All right, so if 0 and 1 are complements of each other, then x dot, or I guess 0 dot 1, because x apostrophe is the complement of x, 0 dot 1 should be 0 according to this. So again, it can't be that, but this is 0. 0 dot 1 dot 0 is 0. Okay, okay, okay. But also something dot 1 should be the something back. Okay, something dot 1 should be the something. 1 dot something should be the something. I think that this first column is the other operation. I think that if we let the logical question are both values asserted be represented by the dot operator, that again, we can satisfy the Huntington postulates. Hmm. And in fact, yes. If we have two Boolean variables, call them x and y, they each can have only one of two values, 0 or 1. If x and y both have the value 0, then x dot y is 0, and x dot y, is doing a pretty good job of representing the answer to a logical question. Are all of the inputs x and y 1? We represent a logical yes with the value 1. We represent a logical no with the value 0. And there's the second table there for the T Boolean operator, and there's a small table there for the complement operator, the apostrophe. I'm just going to call it the complement operator. When we just toggle, right? If x has the value 0 and we want its complement, then we should use the other value. There are only two in our binary Boolean algebra. Binary logical algebra, as opposed to what I erased, and that's the arithmetic part of it. Note that this symbol is familiar to us, but it does not mean addition. 1 plus 1 is not 1. 1 plus 1 is 2. This is not addition. And this is not multiplication, although it kind of looks like it. These are not numbers. They are logical values, yeses and nos, asserted and not asserted. And those are the things that we're going to algebra with. Because the algebra that we're developing, and I think I can stop sharing the screen at this point. because of the way that we have defined our two-valued algebra, representing the answers to logical questions, yeses and nos. There is a really sort of robust, sort of natural application of the work that we've done to propositional logic. For example, I'm recording this video on a Sunday. Suppose I were to claim that it is Sunday today, and this marker is red. Because my statement contains two logical claims that it is in fact Sunday and that this marker is in fact red. The overall logical truth is the thing that I said, true or false, depends on the truth or falsity of the two claims that I've made. It is Sunday today, and this marker is red, is not true, because it is not true that this marker is red. This marker is blue, and today is Monday. It's not true, because today is not, in fact, Monday. This marker is red, and today is Monday. Is also not true, because neither of the things is true. The only way I can get a full, complete, logical statement about one truth, one logical statement, and another logical statement. This marker is blue, and it is Sunday today. The only way I can get a statement that combines two logical claims with the word and to be entirely true is if both of them are true. So how do I get a statement? Let's talk about this case. It is Sunday today, and this marker is red. What do I have? I can't use and. I have to use some other way to combine those two logical claims. And I start to think about the, other words like and, other conjunctions that let me combine two statements. It is Sunday today, but the marker is red. Well, but what does that mean exactly? It's Sunday today, but the marker, well, it isn't red. What? Okay, that's confusing. What are, and, or, but, nor, Trying to think of other conjunctions in English. But wait, or hold on. It is Sunday today, or the marker is red. Now, it's true. You're right that the marker is not red. That part of the claim is false. But I did say a true thing. In other words, my logical statement, it is either true that it is Sunday today or that the marker is red is accurate. You know, one of those things is true. It is either true that it is Monday today or that this marker is blue. Still, on balance, true, because only one of them has to be true. It is either Sunday today or the marker is blue. Well, one of them is true, so it doesn't really matter about the other one, although they are in fact both true. The only way I can get it to be totally logically false is if I say two false things. It is Monday today, or this marker is blue. It is Monday today, or this marker is red. Neither of those things is true. So it is not true that either it is Monday today or that this marker is red. That because the reason, so x t y, like what, it's not plus, so I don't want to use, like, plus to me feels arithmetic, but it's not arithmetic, so I don't want to call it plus, but that's clearly a plus sign, so what the hell do I call it? And the answer is, well, call it the or operator, so we can read this expression as x or y. We can read this expression as x and y. That when we see this, the symbol dot is representing the idea of and, that the symbol plus sign is representing the idea of or. And the complement, x with an apostrophe, is representing the idea of not. Not that, right? Okay, here's thing. What about not thing? The complement. Suppose we constructed for ourselves digital electronics. Digital electronics that when we input signals, logical signals, when this signal is asserted, it has a higher signal level than when it is unasserted, representing logic value 1 and logic value 0. Suppose we developed electronical elements that took two inputs and that the output was the and operation. And think back to regular algebra. Sometimes we write the multiplication dot. Sometimes we just smash the two letters next to each other and that's multiplication. So here again, I'm going to use the same convention. This is looks like multiplication, and therefore looks like the dot Boolean operator, which looks like the and operation. So this is x and y. And suppose we had another one that gave us as an output another signal that we can track whether its value is high or low, asserted or not. Those feel like they would be super useful, and that we would want to make digital circuits with those all the time, so that we would want to have a reliable way to represent that circuit element in a picture. So we can just draw it and say, yeah, okay, that's that thing. A hemisphere will be our symbol for the and operation. And this sort of like rocket ship looking thing will represent the OR operation. We're going to call these electrical elements gates. So each one is a gate, and we have our inputs and an output. Each of these are signals. We could use this signal as the input to another gate if we wanted. But each time we see a gate, it's doing the thing that it represents. The hemicircle, the semicircle is and this sort of spaceship thing is or. This content was actually introduced at the end of the chapter 1, for, which I guess just kind of as a preview of what's coming in chapter 2. But now we have this whole wide world of Boolean algebra available to us. If we have Boolean variables that, we have operators and an OR to manipulate, what exactly what are we able to do? How is that useful to us? Can we do that thing I was talking about at the beginning of this segment about, Boolean functions and having them do different jobs for us? Could we define different electrical gates that correspond to circuit elements that are doing those different logical jobs, those functional jobs? Let's find out. Next segment.